స్టార్ట్ చేద్దామని చెప్పి అడిగారు.
Live streaming.
Yeah, live stream is now on, sir.
Exactly.
Yeah, now it's on.
Yeah, shall we start?
Yes, sir. Ratna sir, can you share that live stream link?
Raju garu.
Meanwhile, Chaitanya, you can initiate, brother. You can start.
Yes, sir.
Chaitu, you have to unmute yourself.
Yeah, I've done it, sir.
Yes.
I request respected participants, please look at the chat box. That is the YouTube live stream link. Please open the YouTube live stream link in separate window, and please mute volume in YouTube video, YouTube live stream.
Chat box link is there. Yes. Open a new tab.
Yes, sir. It's already live is activated, sir. It is opening.
Now can we? Chaitanya sir, please start, sir.
Hello?
Sir, 1 second, sir. Chaitanya, please start.
Yes. Start. I think full of
Chaitanya sir, మీ ఆడియోని అన్మ్యూట్ చేయండి.
Raju garu, ఆయన అన్మ్యూట్ లోనే ఉంది కానీ నాట్ నౌ ఇట్స్ అన్మ్యూట్. యా.
refreshing and of CSE and
Not able to hear
the
anything.
departments
Not able to hear anything.
Chaitanya, not in a position to hear anything. We are unable to hear anything. Sir, sir.
Sir, unable to hear, sir.
చైతన్య సార్, మీరు ఆడియోని సెట్ చేసుకోండి.
అదే చైతన్య చెప్పండి, ఏంటి ప్రాబ్లం?
చైతన్య
చైతన్య సార్, మీరు యూట్యూబ్ స్ట్రీమ్స్ క్లోజ్ చేసేయండి సార్.
సార్, మీరు యూట్యూబ్ స్ట్రీమ్ ని క్లోజ్ చేసేయండి.
సార్
సార్ యూట్యూబ్
shall I continue?
Yeah, please. Not at all audible, Chaitanya.
Yeah, shall I continue, sir? Is it audible?
Now it is okay.
Now it's okay.
Okay, now it's okay.
Yeah, good. Okay.
Yeah, I'll be starting again, sir.
Yeah, please.
On the behalf of the management of CSE and staff of MGIT, I take it all for this one national DP on the role of machine learning and data science in artificial
Chaitanya, there's
intelligence.
some problem with your. There's some problem. There's some problem with your.
It is a very wide applications ranging from it's still
So Ratna, we will do one thing. So just Chaitanya, you mute and the principal sir will take over, and the guest speaker will start.
Yes,
So
sir. Sure, sir.
that's better.
Sir, good morning, sir.
Morning, sir.
Good morning. Good morning.
Good morning, all the guests, participants present today. Professor Ramanamurthy Garu, Professor C.R.K. Reddy, and on behalf of MGIT, I welcome Professor Somayajulu sir for this FDP program on machine learning and data science role in artificial intelligence, jointly conducted by Department of MNH and CSE of Mahatma Gandhi Institute of Technology, Hyderabad. Mahatma Gandhi Institute of Technology is one of the premier engineering colleges in the self-financing category in Telangana. It was established in the year 1997 under the aegis of Chaitanya Bharati Educational Society and is affiliated to Jawaharlal Nehru Technological University, Hyderabad. Institute has received accreditation for eligible 6 UG programs for 3 times from National Board of Accreditation, New Delhi, and MGIT also is accredited by NAAC with A grade. The institute offers 8 undergraduate degree programs and 6 PG programs, and from this academic year onwards, institute has got extension of approval from AICTE for starting 3 UG programs in the areas of artificial intelligence, machine intelligence, data sciences, and computer science and business systems, and 1 PG program in artificial intelligence. Sir, for information, the institute has received MHRD's NIRF 2020 ranking, and we are in the rank band of 201 to 250, and it is a constant effort and the untiring work that our young staff at MGIT are indulging in from day in day out, that we could able to enter into the NIRF 2020 ranking. And on behalf of my entire teaching fraternity of MGIT, I would like to share to all of you that we have set a goal. By next year, we would like to achieve a ranking below 150. And I wish all my young staff, all the departments of computer science and engineering, information technology, electrical and electronics, electronics and communication, mechatronics, metallurgical and materials engineering, civil engineering, mechanical engineering, and the upcoming new EG programs in artificial intelligence and machine learning and data sciences and computer science and business systems to strive for this particular goal. And I wish all the participants who are going to join today for this 5-day FDP derive ample inputs in terms of nurturing their interest in machine learning, data sciences that are very much needed for artificial intelligence to be inculcated in their regular curriculum, as well as to carry out in pursuit of being part of Make in India program of Government of India. Thank you very much, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir, for a brief message. To the party convener of the FDP to address the participants. Over to you, sir.
Chaitanya?
Murthy sir, మీరు స్టార్ట్ చేయండి సార్.
Yeah, good morning to everybody. Respected Principal Mr. Jayashankar Garu and the chief guests of the today's inaugural function, Professor Somayal Garu, Real and Somayal Garu, and Professor C.R.K. Reddy, and my distinguished colleagues of the college, distinguished colleagues of our MGIT, and the distinguished participants across the globe. I take the privilege to welcome you for this event. And you know very well, the event is named as Machine Learning and Data Science, their role in AI. That is basically these two are like two hydrogen ions in a diborane structure. So they are going to support the entire AI for the ML as well as that machine learning as well as data science. You know, machine learning is basically concerned with automating the automation and getting the computers to program themselves and writing software in a bottleneck and making the data to do the work instead of somebody doing. So therefore, there we need to depend on what you call how we can represent. The representation of the machine learning is makes a lot of makes a lot of effort for creation of artificial intelligence. In that we use some concepts like decision trees and then set of rules, instances, graphical models, and neural networks, neural networks, etc. So all these things are going to be covered by our distinguished speaker. Today's speaker we have Dr. Bharat. He is from University of Texas, working with the IBM research group and is a research scientist heading the research scientist group in that. So we welcome you, and I wish all the participants to have a what do you call better stay and receive the best from the all the resource persons, and best of luck. All the best. Thank you. Thank you, sir. Next, Professor C.R.K. Reddy.
Okay, sir. So,
Sir,
good morning, one and all.
Very
This
much
is Dr. C.R.K. Reddy. Okay, good morning, one and all. This is Dr. C.R.K. Reddy on the behalf of Department of Computer Science and Engineering, Mahatma Gandhi Institute of Technology. I welcome our each and every participants and our namaskarams to chief guests and respected principal, sir. And now I don't want to come in between you and the guest of speaker. So now I request Dr. Somedul sir to address the gathering. Over to you, sir. Dr. Somedul sir, please kindly take over, sir.
Yeah.
Thank you.
Good morning, everybody. Principal of the MGIT, Hyderabad. Am I audible?
Yeah, you are audible, sir.
Yes, sir.
Yeah.
Very
Okay.
much.
Thank you.
Please
Thank
continue,
you.
sir.
Principal, MGIT Hyderabad, Professor Jayashankar, Ramamurthy Garu, coordinators, and today's chief guest from abroad, and participants, faculty of MGIT from various departments. Very good morning to all of you. First of all, I thank Professor Ramanamurthy for giving me an opportunity to speak as part of the inaugural function of this workshop, or in other words, a faculty development program on machine learning and data sciences. So I would like to give briefly about the importance of these areas. As mentioned by Professor Ramanamurthy, data science, machine learning are all part of AI, and deep learning is also part of AI. In fact, each subcomponent is a subset of AI. Compared to traditional AI, today's AI is totally different. And you all know that already Government of India released a white paper on AI, and it is now recognized as a highly critical growth area with impact across many sectors, including science, government, finance, healthcare, manufacturing, advertising, retail, and others. AI might just be the single latest technology revolution of our lifetimes, with the potential to disrupt almost all aspects of human existence. You all know that the co-founder of Coursera, Andrew Ng, and formerly head of AI group, Google Brain, compares the transformational impact of AI to that of electricity 100 years back, with many industries aggressively investing in cognitive and AI solutions, and global investments are forecasted to achieve a compound annual growth of 50.1% to reach 57.6 US billion dollars by 2021. AI is not a new phenomenon for all academicians. It is a worldwide new battle only, with much of its theoretical and technological underpinning developed over the last 70 years by computer scientists such as Alan Turing, Marvin Minsky, John McCarthy. AI has already existed to some degree in many industries and governments. Now, thanks to virtually unlimited computing power and the decreasing cost of data storage, we are on the cusp of the exponential age of AI. As organizations learn to unlock the value trapped in vast volumes of data. That means ultimately, from the business point of view, whatever the type or kind or amount of data that is available with the organization, how quickly you get insight by using innovative performance-oriented models. So all these things coined as part of machine learning. AI is a constellation of technologies that enable machines to think or machines to act with higher levels of intelligence and emulate the human capabilities such as sense, comprehension, and act. That means decision making also should be automated. Thus, computer vision, audio processing can actively perceive the world around them by acquiring and processing images, sound, and speech. So that means what I want to say is AI for all now. AI is everywhere. As part of the new AI, our machine learning and deep learning, data sciences, they are all part of this larger system. AI system can also take action through technologies such as expert systems and inference engines, or to undertake actions in the physical world. You all know that there are different categories of AI, but from the comparison point of view, I would like to explain three simple categories: weak AI versus strong AI. First one is, how do we compare weak AI versus strong AI? Weak AI describes simulated thinking. That is a system which appears to behave intelligently but doesn't have any kind of consciousness about what it is doing. For example, a chatbot might appear to hold a natural conversation, but it has no sense of who it is or why it is talking to you. Whereas strong AI describes actual thinking, that is behaving intelligently, thinking as human thinks, with a consciousness and subject in mind, or in other words, subjectiveness in the mind. For example, when two human beings converse each other, they most likely know exactly who they are, what they are doing, why they are doing. So this is how weak AI and strong AI can be comparable. Then there is another kind of categorization called narrow AI versus general AI. Narrow AI describes an AI that is limited to a single task or set of number of tasks. For example, IBM's Deep Blue, the chess playing computer that beats world champion Garry Kasparov in 1997, were limited to playing chess. It would not have been able to win a game of tic-tac-toe or even how to pay. But whereas general AI describes an AI which can be used to complete a wide range of tasks in a wide range of environments, That means different types of environments are taken into consideration. As such, it's much closer to human intelligence. So in a way, generally I consider as closer to human intelligence. Then there is a third kind called superintelligence. The term superintelligence is often used to refer to general and strong AI together at the point at which it surpasses human intelligence, if it ever does. While big strides have been made in artificial narrow intelligence, wherein algorithms that can process documents, drive vehicles, or beat champion chess players, no one has yet claimed the first production or development of general AI. Therefore, it is good that um, the college MGIT has started a program by inviting experts from abroad to train the faculty members on the current areas of machine learning and data science, which are part of AI. But you know that AI is applicable everywhere, as I mentioned, in healthcare sector, agriculture, smart mobility, then retail sector, then manufacturing, energy, smart cities, etc. In fact, education and skilling is also a very important area today. AI can also potentially help to solve the quality and access issues observed by in the Indian education sector. Therefore, I am happy and also I congratulate the entire organizing team of the Department of CSE, MGIT Hyderabad, and other sister institutions for organizing this prestigious program. As principal mentioned, this is a very interdisciplinary course wherein all engineering students should learn and then pick up best skills for better employment and better opportunities. With these few introductory remarks, I thank you all for giving an opportunity to speak on as a part of inaugural address under this FDP program. Thank you all.
Thank you, sir.
Thank you, sir. Thank you, Somayal
Thank you,
garu.
sir. Thank you very much.
Thank you very much, sir. Somayal garu.
Thank you. Thank you.
Thank you, sir.
Now, shall we move to the introductory speech, sir,
Yes, sir.
by the
Yes, sir.
director?
Let's see introductory speech. Please.
Thank you, sir. Thank you, sir. Thank you very much, sir.
Thank you. Thank you.
CRK. Professor CRK.
Extend a very cheerful vote of thanks to Bharat sir.
Sir, chapman, sir.
Look, start it. No problem. Go ahead. We expect. Okay, Chaitanya will come in introducing the other. Resource person. Kindly go ahead. Please go ahead. Sir.
Thank you very much for your valuable and informative message. Today's resource person, Dr. Bharat Danda, staff member in
Chaitu, you can switch off your video. You are not audible, first point. Ratnaraju, just mute chases or
welcome this person, Dr. Bharat Bandala. Bharat Bandala is a research staff member in the and Life Sciences Department at IM Research. Dr. Bandala joined the original vaccine research team in 2013 after the team won the Jeopardy TV show and shifted the research focus to adapting vaccine for the healthcare domain. His area of specialty includes machine learning, natural language processing, and clinical informatics. Prior to joining IBM, he received PhD Masters in the US from University of North Texas. With this views, I'd like to invite today's resource person, Dr. Dandala. Thank you very much.
Thank you, Chaitanya. Now, Dr. Can I request you to kindly take over, sir? Yeah.
Hello, everyone. Good morning. It's actually past midnight here for us. First of all, thank you for the opportunity. It's an honor to present about my research as well as our group's research and what we are doing here at IBM. I would like to start by saying thank you so much, Dr. Ramanamurthy sir, for giving this opportunity to me. It's an honor to present to your faculty of the esteemed university, as well as to your students. Thank you. So today I'm going to talk about what is artificial intelligence, or what is NLP, and how it is making a big difference in the field of clinical or healthcare. So, and also briefly introduce about my research and what I have been doing for last 8 to 10 years or 13 years. So the topic for today is artificial intelligence for healthcare. And about me, I'm a research scientist at IBM Research. And I have a PhD and master's in computer science from University of North Texas. I finished my PhD in 2013, and I joined IBM Research in the year of 2013. So before that, I did my bachelor's in Srinidhi Institute of Science and Technology, so which comes under, of course, JNTU. My research interests are artificial intelligence, and from last few years, my focus shifted to what natural language processing can do in the healthcare or in the clinical domain. So currently, I am in New York. I have been hearing a lot in the news about all the COVID-19, etc. So this is about me, like where I was and where I am now. In the great introduction given by Dr. Soumya Julligaro about saying about Deep Blue and IBM computer that beat Mr. Kasparov. So, and following that, like IBM tried to do another grand challenge after beating the chess player, is actually going and participating in the Jeopardy challenge and have an NLP or AI question answering system that can answer the questions asked in the challenge. So I was part of the team. So briefly, because like the challenge was in 2012, I joined IBM Research in 2012, and then we started to focus. So I joined the same team. Then we started to move our focus or shift our focus towards bringing clinical NLP or bringing IBM Watson into the clinical domain. And also, we tried to do a lot of open domain question answering for different types of questions that were not encountered during the Jeopardy challenge. So those were my two research areas, and that I was focusing on from past few years. So I'd like to say about like electronic health records. So this is very common in most of the developing and also the developed countries. So this shift has happened from paper-based patient records to the electronic health records, and the objectives of that is contain. Someone saying something? Sorry.
Please go ahead. Go ahead.
Okay.
Don't worry. Please go ahead. Go ahead.
Yeah. So the idea is to contain the information, which is basically store the information about the medication history or diagnosis or treatments of the patient that were given, and allow access to evidence-based tools that can provide help to the patient's healthcare, and also to automate and streamline the provider workflow. So these are the three objectives with which electronic health record systems or electronic health records have been started, and a lot of countries adopted electronic health records. But there are several issues with the electronic health records. So the major issues are lack of interoperability between information technologies or EHR and EHRs, and it is expensive to set up and maintain, and drop in physician productivity because of adapting to the latest technologies, And this may come as a shock to everyone. So actually, the EHRs increase the workload on the physicians because with the EHRs, much more documentation is required for physicians before, during, and after the patient visit. So, and also to alleviate these issues, several small technologies have been developed, and one of them is like copy pasting or macros, templates. But this has bloated the information that is in the electronic health record because to save time, so the doctors have been mostly copy pasting the information from previous notes or previous visits. So this puts the patient safety at risk and impairs quality of care as updates or changes between visits can be overlooked or not even documented properly. So what does this lead to? So one of the bigger issues with electronic health records and the amount of time it is taking for physicians or doctors to really write it. So it is estimated that at least 35% of physicians in developing world, and also, of course, 50% of physicians in the United States, because in the United States, considering the legal issues surrounding the healthcare, so you have to clearly document everything that happens within each and every individual visit. So this is causing a tremendous amount of stress on physicians, and there is a lot of burnout. So physician burnout is negatively associated with many things like professionalism, altruism, and quality and safety of care. So at the individual level, physician burnout has been associated with cardiovascular diseases, alcohol use, depression, suicide, stress, etc. Burnout has also become a complicated, also have like adverse financial effects on the indirect adverse financial effects on the practices and the organizations involved. So here are some of the major contributing factors of burnout. So EHR, as you can see, like it is contributing the most. So the total amount of from the total amount of burnout, 21% of burnout is coming from just using EHRs. And among those, the biggest factor is writing the notes, which is notes, the 33%, because it takes a tremendous amount of time to document the notes. And the other bigger chunk is 14% coming from like basically reviewing the charts before the visit. And lack of information is causing a large amount of stress to the provider, as well as have potentially negative implications on the health of the patients. So what can be a potential solution that can alleviate these kinds of issues that we are suffering today with the electronic health records? So as a grand challenge, after IBM Watson, we started adapting or moving the whole IBM Watson into healthcare. So that started in 2013. So we have been working on these systems or as a grand vision for the future to alleviate the potential implications.
Excuse me, Bharat sir.
Yes.
Hello?
Yes.
Bharat sir, you are not, your frame has been freezed, sir. Like audio, you are getting it, but video, we are not able to see you and slides also.
Oh.
So can you?
Is it same for everyone?
Refresh your... Yes, sir, for everyone, sir.
Okay.
Can you refresh yourself, sir, or you can rejoin?
Yeah.
Thank you. So technical team, kindly take charge. If some issues are there, let the speakers know, and otherwise it will be...
Sure, sir. Sure, sir.
Thank you.
Bharat?
Yeah. Meanwhile, we can announce that the speaker will be rejoining shortly due to frame refreshment rate is slow. So I request all the participants to kindly... Yeah, now it is fine.
Yeah.
Now it's fine, sir.
Okay.
Please continue.
So the overall idea, I think I have to share my screen. You can see my screen, right? sir?
Yes, yes.
Okay. So the overall idea is like, can we build a potential solution that can alleviate these kinds of issues? Okay. So what our grand vision is basically, can we develop a solution that can be problem-oriented summarization? So can we develop a summarization system with which the doctor can quickly get the information that he really wants at the point of the care? So the idea is, first of all, the patients may have like a lot of problems. Like, so this is one patient. It's a Jane Doe. So it's a de-identified patient, but this patient has a lot of problems, like GERD, to diabetes, to hyperlipidemia, obesity, etc., etc. So he may have to see a lot of specialists over a period of time, and he may have to get like a lot of his visits from his primary care physician. So the idea is to centralize and build a problem-oriented patient record summarization. So as you can see, so these are the problems that were extracted. I will talk about it in more detail, like what NLP and what technology that we have used to develop this system. So the problems that you see on the left side are all the problems that the patient has. And once the doctor comes to a visit, and then these are, as I said, like these are automatically generated. So once the doctor is kind of knows like what the patient is for today, now if he knows like, okay, he's here for diabetes. So if he clicks on the diabetes, if you can highlight or extract all the information that is related to diabetes, like insulin, liraglutite, metformin that the patient is on, and what are his lab results, and what are his lab values, and also what are the potential orders or like the procedure orders that we have that the doctor has prescribed to the patient. So if you can list that helps doctor solve like 50 to 60% of the information needs. So what is the next step? So now let's say the doctor is not happy or he needs more information what happened with the patient. Now if he selects and digs down a little bit to the diabetes mellitus type 2, now he has another dashboard like where he can see over a period of time what happened to A1C goal. So what happened to his A1C levels? So his goal is to maintain the A1C less than 7%, but he tried to maintain that from 2011. So you can see the summary and what happened to the patient's A1C level. And also you can see like a lot of medications, what are the medications that he is on and which are related to only diabetes mellitus, labs, weights, and blood pressure. And also the most important thing is summary of last visit. So sometimes all the doctor wants is to know what happened in the last visit. But at the same point of time, the notes that are written are so long, like you can have like 400 to 500 sentences in each of these notes. So the doctor doesn't have that much time to go through the whole note. So what can we do? So we can develop solutions that can extract the information and provide a second summary of information that the patient can really go through, that the doctor can really go through at the point of care. Now let's say this is not enough. Now doctor wants to go deeper. So one point that I want to add here, from the summary, you can actually able to identify reason for increased A1C without reviewing the whole note. So that's the whole point of summarizing the note. Now he can also dig in, okay, what happened to his endocrinologist? So now let's say he wants to do one more. So these are all summaries that were extracted. These are not the actual note. The actual notes are so long, as I was saying, they are like 1,000 lines or 2,000 lines, but the doctor can just go through this and get all the information needs that he has. Like all he has to know is like, okay, what happened and what is the treatment plan that was prescribed for the patient before in the last few visits. And also, once you know what are the medications that he has, now the doctor has to know one of the biggest issues, right? Like adverse reactions or adverse drug reactions is one of the most important issues that the whole healthcare runs around, because like your approvals or medications, anything surrounds around adverse drug reactions and the studies which are clinical trials that are related to it. But from this information, like the doctor can really know what are the adverse drug reactions that the patient has. So if you can extract this information, these are in like, before 5 years, 2 years, 3 years. So as an example, in 2011, the patient was on metformin for diabetes and he was getting diarrhea. And doctor doesn't really have time to dig and go and read all the information. And also you are switching between the doctors, and patient doesn't know much about what metformin is, what diarrhea is, etc. So if you provide such an information, now when the treatment plan is provided, doctor can provide a much better healthcare to the patient. So that is the overall idea. Now, let's say you still need to go and dig more information. You can provide like search technologies. Search technologies like Semantic Find, which is tailored towards electronic health records. Now, the doctor wants to know about the medication Liraglutite. So he searched for Liraglutite, and he gets like a bunch of notes where Liraglutite is mentioned. And also, the most important point is, it's not only Liraglutite, but it's Victosa. Victosa is a brand name for Liraglutite. So if you can extract and show information like that, that will help a lot. So this is one use case of Semantic Find, but there are many others which I will show here. So now, when the doctor sees, okay, I saw like, okay, so there is a worsening HTN that is mentioned in the in this note, which is like worsening hypertension. Now I want to go dig deeper. I don't want to search for worsening HTN. I will search for HTN. HTN is basically hypertension, which is another big point in the clinical notes. There will be a lot of abbreviations that are mentioned. So now, as you can see, the doctor typed in HTN, but there are many things that came out, like which is blood pressure was very high, blood pressure 184/72. So blood pressure 184/72 is an indicator for worsening hypertension. So such a connection can be made only if you have a very good NLP technology that can potentially understand clinical notes and potentially tailor towards the clinical notes. So now you want to know more information, like let's say this is another example where you provided like difficulty in breathing. So you saw shortness of breath, dyspnea, etc. But this is, so let's say the patient comes in and he says, okay, I have difficulty in breathing. You search for it and you found it only once. It's not even mentioned. And the most of the times it is mentioned, so there is as negated. So it's not a positive mention, as you can see here. Sorry. As you can see here, 12 matches are basically for negated. So that means most of the notes are basically saying no dyspnea, etc., which are almost like a boilerplate or template stuff the doctors use when they write the notes. So my point is like the whole point is to build on like what we actually need. So to do such a solution, what do we need? So those are the technologies that depends on NLP and AI, which I will introduce now. There was a great introduction provided by the speakers already about NLP and what it can do, but I will just summarize in like 1 or 2 words, which also relates back to my research back in when I was a PhD student. So NLP refers to a language spoken by people like Telugu, English, Japanese, as opposed to artificial intelligence languages or artificial languages, sorry, like C++ or Java or C. Natural language processing is a technology that used to aid computers to understand the human natural language. The technologies are, as you know, like one is IBM Watson, Apple Siri, which we use, or even Google Search, which is basically information retrieval. And also there are several NLP technologies behind it. While humans can easily master a human language, the ambiguity and imprecise characteristics of the language make NLP difficult for machines to implement. So here is an example. I can hear bass sound, which is like a music. He likes to eat grilled bass, which is a fish. So a lot of people can easily sense it. I mean, humans can sense it. Okay, these two are two different bass. One is sound. I know it's a music because there is a word sound and hear. And when I see eat, okay, I know it's something. It may not be a fish, but it's something that is eatable. So these two are two different bass. So I want to provide this one example because my PhD is on word sense disambiguation. So this is the ambiguity in the language and how NLP can address the ambiguity and resolve this ambiguity is a bigger problem. So that is where the AI started, and that is where AI stopped in 1960s, and that is where again AI started in 1990s. So the whole NLP AI surrounded around one problem, which is ambiguity in the language. So in 1960, they said, yeah, we don't have a system that can really understand whether this bass is fish or whether this bass is music. So now we want to move the field in a different direction, which is basically building the knowledge sources and let's see if we can build systems which are machine learning or NLP in the future. So from 1960 to 1990, most of the efforts were in building the resources like WordNet, which is one of the most important one for LISC, and as the technology went by, Wikipedia has become a bigger resource for all the NLP technologies that was built over the past few years. So, as I already introduced, clinical NLP is little complex than the actual NLP, because clinicians are, as I said, like they're extremely busy. Their note structure is really different. So this is a note. So this doesn't even look like any of the papers or any of the documents that we really see, which were, most of them are really well written. But clinician notes or physician notes are really not well written. So it's kind of like, I don't want to use the word mess, but it's a mess. So you can see there are several structured imports like medications and the physical exam, and a lot of abbreviations that were used. Only the physicians can understand. Like, for example, PT means patient, and HGB-A1C is hemoglobin A1C. So these kinds of abbreviations are very, very, you can see them with highest frequency in clinical notes. You won't see it in any other types of notes. So some of the basic NLP things that in clinical NLP are identifying the diseases, such as like diabetes and HTN, which is hypertension, which is an abbreviation in this case, and also identifying the modifiers like stopped, started, a medication, and also linking them to the UMLS or Unified Medical Language System resources, which is basically an entity linking problem. So which is basically normalizing the mentions that are mentioned in the note. The other problem is relation extraction, which is another well-known NLP problem, but this is all tailored towards clinical NLP. So what do you want to know? Like whether something causes, whether something treats. So metformin treats diabetes, but metformin actually causes nausea or fatigue, like when it is taken with care. So, and also, as I was saying, like you want to extract these modifiers. So once you know like what happened to a medication, like, stopped or started, etc. So that can actually help a lot of, provide a lot of information for the doctors. Okay, why did it? So once you know it stopped, okay, then you can go dig in and see like, okay, why did the doctor stop? Why did in that visit they decided to stop this particular medication? Okay, there may be an ADE. So this is the information that the doctor wants to provide better care. So, and another well-known, so these are all fundamental technologies. So abbreviations, as I was saying, there are a large number of abbreviations are ubiquitous in the clinical notes, like years, YRS, year-old, YO, or SAH, etc. And headache, HA, nobody knows HA is headache except for the doctors. And this is like an architecture that we have built over a period of time. So as I was saying, this is all coming from IBM Watson, and from the IBM Watson, we kind of our whole research team shifted to IBM Watson Medical, and now it's called IBM Watson Health. Okay, so this is still built on like a lot of fundamental technologies that were used in IBM Watson, like Apache Uema or DUC, which is Apache Distributed Uema Clustering Computing. These are all available for free, which are Apache licensed, so anybody can use for free. So the overall idea is like the electronic health record has both structured data and unstructured data. So the structured data has the medication, procedures, labs that are available as databases. So the patient has a database, but the unstructured data is written by the doctors, which are clinical notes. So we wanted to build a pipeline that can basically process both structured data and unstructured data and extract the information. So that is the overall vision of the top part of that. And the bottom part is like basically taking the structured data and unstructured data, what are the NLP technologies or AI technologies that we can build? So as you can see in the bottom of the image, we, as the field is progressing, we build these technologies. So we had rule engines, like which is in, I don't know, 1995 or 98. IBM had a team that was working on NLP. They continued, and then we built feature-based machine learning algorithms, like which are which depends on techniques like naive or support vector machines, etc. As the field passed by in 2012 or 13, so deep learning made a comeback because I attribute a lot of the success to the computers that have become faster rather than these technologies being innovated at this point of time. So the computers are faster now. So deep learning technologies made a comeback because the models can be learned faster. So at the time we had the ideas, like all the people, experts in NLP had ideas back in 1970s, 80s. But at the time we don't have computers that can process that faster. So with the GPUs, TPUs that are available now, so we also built like several of these technologies using deep learning. So there are 3 layers to it to make it easier. So it is segregated into 3 layers. The fundamental technology, which is basically recognizing the tokens from the text or sentences from the text, parts of speech tagging, semantic parsing, extracting the named entities in the text like diabetes or hypertension, resolving the abbreviations and disambiguating these abbreviations. So whether, as I was saying, like abbreviations can have multiple expansions, so you have to find the right expansion based on the context, which is a sub-problem of word sense disambiguation. So you have relation extraction, which is recognizing the relations. So the next level is basically very tailored towards clinical documents, like how do you extract goals that are mentioned in the clinical document? How do you extract plans that are mentioned in the clinical documents? Or you want to know whether so assertion is basically what is the belief status of the physician when he wrote a note, like is the medication being started, or he said no dyspnea, or he said hypothetically may patient have dyspnea, which is kind of like hypothetical. So can you extract these kinds of information? And the note sections is like, as I was showing the clinical note, you have multiple sections like procedures in one section, medications in one section, assessment and plan in one section. So, but this is not like a fixed format. So you have to extract or identify these sections basically using some NLP, or so as simple as like, okay, you can write few rules saying, hey, if the section starts with PMH, then I believe it's a PMH section. If the section starts with A and P, then I say it's an assessment and plan. And you can go as complex as deep learning models, like where you can take the advantage of sequential sentence learning models, or you can go feature-based models, like where you use a CRF or a conditional random fields, basically, or to train these models. So there are various technologies, various options that we have built for each of these problems. If you go one level up, so which is the overall view that we actually saw in the first few slides. So you want to generate the list of problems, and you want to provide a consolidated medication timeline, semantic find, like where people can actually search if they need more information, extractive summarization, which is also known as textual summarization in the open domain NLP, and you want to identify the relations between the mentions that are in the structured data, which are medications, and the problems that you have extracted. Sorry, I'll take a pass. 1 second. Okay. So now we saw like a broader picture of what these NLP technologies are that we have in IBM, and also what we have built as a research team over the period of years. Now let's dig little deeper and understand one such problem. So because considering the time we have, so I would like to dig down into one problem and show like what we have developed and how it can potentially make a difference in the future. So the topic that I will focus today is adverse drug event reaction extraction, because adverse drug reactions or adverse drug events are like is one of the most important things that is considered as one of the most important things in the field of clinical domain. So just to give a broader picture, this is what it is about. So you take a medication, you get the adverse reactions. You take the medications for, let's say, diabetes, but you get, dizziness, you get sweaty, you get confused. Now, you don't even tell the doctor, because you don't even know this is an adverse reaction that is caused by some medication. So maybe after 1 month or 2 months or few months, you continue to take that medication. Then you may go to a doctor And the doctor asks, hey, what happened? Like, did you feel anything bad, like over the period? You will say, yeah, sometimes I felt dizzy, or sometimes I had nausea, etc., etc. So the doctor writes that. So the doctor writes and notes, okay, so the patient has nausea, okay, I'm reducing the dosage, or I'm completely stopping the medication. Now, after 5 years, you continue this medication, but the doctor never tells you, I reduced your dosage. He will just tell you, yeah, I am writing a different medication for you. Now, after 5 years, you will see a new doctor, and now that doctor can actually increase your medication because he doesn't know what happened before 5 years. So the overall idea is like if we can extract these adverse drug reactions, so we can stop at the point of care, which are basically the biggest problem, the diagnostic errors. So to put as a definition, ADE is commonly defined as an injury resulting from medical intervention related to a drug. ADEs are among major public health concerns in both morbidity and mortality. There are several pre-marketing clinical trials, especially in US. There are 3 phases of clinical trials. You have that they observe with animals, then a small portion of patients and a large portion of patients, then they release it to the market if the FDA approves. But then begins the bigger thing, which is the post-marketing surveillance. So let's see on a larger scale what's going on with this medication. So then the FDA can, stop a particular medication from the market and call out, and it can make a recall of that medication. So there are spontaneous reporting systems such as FAIRS, where the physicians or patients are also the medication vendors can actually go and report the adverse drug reactions that they have observed. However, previous studies have exposed various inadequacies because it's underreported. There are biases because it may be good for the most common diseases, but for the rare diseases, maybe only 1,000 or 2,000 people have the disease in the whole world. Now, who knows like what happens to them like when they take this medication. Several efforts have been made to automatically extract from disparate information sources, but they are all mostly like they are helping the cause, but they are still evolving. So I'd like to specifically talk about 2 challenges that we have participated as a team. So the first challenge was organized there are many challenges that we have participated over the period of time in the recent years, but with respect to adverse drug reactions and the clinical documents, there were 2 challenges. One is organized by Massachusetts University, and the other one is organized as a challenge continuing the I2P2. So this is pretty much related to EHRs and can you extract all these adverse reactions and how you can make the healthcare better. So in the MAID challenge, we have so this is all coming to mostly towards AI. We are stepping away from the introductory part. Now it's more AI. So it's mostly I'm kind of assuming the listeners know like some of the techniques like supervised learning or unsupervised learning. These at least the kind of things that people do for trained supervised machine learning models. So traditionally for supervised, I'll just give a brief 2-line summary. So for the supervised models, you need to have a manually annotated data set so you can train your models. Just like how you can teach your kid saying, okay, so you show them 10 apples or 10 different kinds of shapes of apples, then they will kind of realize, okay, so the apple looks red and okay, apple has this shape, etc. So you have to show the machines a large number of things so that they can understand. So that is the supervised machine learning. So in the MAID challenge, these are de-identified, which is kind of removing all the patient-specific information because here HIPAA is a big thing. So 1089 patients, longitudinal EHR nodes were annotated, which has like 21 patients from the University of Massachusetts Memorial Hospital. Similarly, there was another data set from N2C to 505 discharge summaries from Medical Information Mart for Intensive Care Clinical Care Database. So these are annotated with drugs, which is like lisinopril here, and reasons, what is the reason lisinopril? So if you read this sentence, take lisinopril for 5 days for hypertension. So that is the reason it's been prescribed, but the patient reported cough. So that is the ADE. And you also have its attributes like strength, route, form, frequency, duration, and the dosage. So the strength is like, what is the 30 mg or 40 mg, or how do you take your medication, whether is it oral or, like through an injection, etc. Or what is the form, is it a tablet or an injection? And what is the frequency? Do you take it like every day or only in the morning or like every 6 hours, etc. So, and also in the other additional part, only in the MAID dataset is also they also identified all the sign or symptoms that are mentioned in the note and also their severity. So for example, patient reports severe cough. N2C2 would not annotate those because they annotated only ADEs and reasons and attributes. But this one, they annotated ADEs, reasons, but also they annotated all the sign or symptoms, which makes little better because you can train better models to distinguish between where a particular sign or symptom is a ADE or a reason versus it's a sign or symptom. So to start with, like there are problems in the clinical documents. So there is a text wrapping, that auto text wrapping that happens in the clinical EHR documents, which puts new line characters all over the place. So there was a wrap around 80 characters. It's not exactly 80, it's around 80. So this goes back to the older systems where you can't exceed 80 characters in a single line. So it automatically puts a new line character, which makes a bigger problem for people who work in NLP because you have to recognize the sentence boundary detection becomes harder. So here is a spacey. If people who work in NLP, they would have heard about it because it is a technology that's out there and people started using it. It's Python, it's easy to use, etc. So if you take that, if you take spacey, then if you just run spacey on this document, now you have like 4 sentences, which is not true, right? You actually have only 2 sentences in that above snippet, but spacey detected 4 sentences. So we wrote rule-based system, very simple rules, whether if particular thing is around 70 to 85 characters, whether I want to replace the new line. If it is not around the 70 to 85, I just respect the new line, and some rules which are very specific to the clinical text. Now, this is the customized spacey. I don't want to go dig in all the rules, but so now we were able to detect these sentences accurately. And coming back to the tokenization. So this is the sentence. This is one of the sentences. I mean, the common way you can see is like a lot of sentences look like this in EHR documents. Albuterol 90 mg 2PF Q6 PRN for 48 to 72 hours. No one knows what it means. That's what it means. Albuterol 90 milligrams, 2 puffs every 6 hours as needed for the next 48 to 72 hours. So that's what it means. So if you give it to a spacey, it did split at 90, but it did not split at 2PF, and it did not split at Q6 PRN. So now, if you want to rely on such a tokens for your NLP system, it is not going to help because your system takes Q6 PRN, but it doesn't understand it has 6 hours as needed. That's what Q6 PRN means. So we customized a rule-based system again, like on top of spacey, built a lot of rules that is for clinical domain. And here is our output showing albuterol 90 mg, 2 puffs. Everything is split. So the red and blue are kind of like the boundaries. So Q is split, 6 is 1 token, PRN is 1 token. So that's how you kind of understand that. So it actually, it's an important problem because so this is what the kind of text that you deal with in the clinical world. So these are some of the statistics around like what are annotated in these data sets. And these are the attributes. These are the sign or symptoms, reasons, and ADEs. And they also annotated severities around these diseases. So, and they also annotate the relations, but the relations are not only in the sentence. So if you see, if you look at this example, so patient presented, patient is kind of remote, presented with trickle bone illness okay, then starts next sentence, started on doxycycline, then starts next sentence, which is patient reports nausea. So now the connection, you cannot rely on technologies that actually do single sentence relation extraction. So you have to go beyond a single sentence. So especially for drug ADE and drug reason. So for ADE relations, 32% of them are intersentential. For reason, 51%, which is almost more than half, are intersentential. So the reason and the drug are not even mentioned in the same sentence for more than 51, for approximately 51% of them. So we started with, again, so how do you represent these things? You have lisinopril 30 mg, so you can use like the begin, intermediate, and outside, tag inside and outside tagging, which is well known, BIO tagging to represent these things. So we started with that. So how do you represent that? Lisinopril is beginning of drug, and 30 mg is begin of strength, and mg continues. So it's an intermediate or inside of the token, and then again a begin of frequency, etc., etc. So this is the representation that we used initially. So we trained deep learning models tailored towards clinical NLP. So we use word embeddings that were trained on a large number of electronic health records. We have parts of speech embeddings. We have dependency tag embeddings. We have character representations, etc. We used by LSTM CRF, which has like the backward LSTM and the forward LSTM and a hidden layer, and then the traditional CRF layer on top to decode the tokens. So that's the overall summary. As I was saying, we used PubMed, etc., plus EHRs and trained the word embeddings to initialize these networks. And we use convolutional neural network for obtaining word representations using all the characters. Then we did relation classification. So once you have that, okay, so now that I have all my entities, drugs, such as drugs, ADEs, and reasons, etc., extracted, now all I want to do is classify the relations. So now we used attention by LSTM, which has the attention mechanism. We used word embeddings and also the type embeddings. So we explicitly said, these are my targets and these are my sources. So lisinopril as a drug, it's a source, and allergic because it's already extracted by your NER component as target codes that we have supplied to the deep learning model. That kind of helped. And this is an attention by LSTM for relation classification that we have trained. Rather than relying only on single sentence relation extraction, we picked almost 7 sentences to get the drug ADE and reason relations. And for the other attributes, because most of them are in the same sentence, only few of them go here and there, the one sentence before and one sentence after. So we picked the neighboring sentences also as the context to extract the relations. But this is a pipeline approach. So we used named entity recognition, and then we used relation classification. NER suffers from lossy representation of overlapping annotations. So here is an example. You have furosemide, you have hypotensive. She is on furosemide on the day of intubation and became hypotensive. So she was taking furosemide and she got hypotensive. She got hypotension. She became hypotensive. That's adverse drug reaction, right? But requiring another medication, which is norepinephrine, which is actually treating hypotensive. Now, going back to our tagging scheme that we used earlier, we actually assign one tag to each and every token, right? Now, we really can't assign a correct token to hypotensive. So do we assign adverse reaction or reason? So if we use pipeline methods, that is one disadvantage. And then intercontextual sentences, intersentential context determine the type of the entity. So in this example, as you can see, so the intersentential context is what determines whether something is a reason or something is an ADE or something is kind of like a sign or symptom that is mentioned in the document. If you look at only presented with trickle bone illness, then you think, if you read only that, then you basically think it's a sign or symptom. But if you read the next sentence, then you think it's a reason. And similarly for the other one. So if you read only started on doxycycline, if you read only patient reports nausea, then you think it's a sign or symptom. But When you read the previous sentence, started on doxycycline, patient reports nausea, then only you think, oh, it's an adverse reaction. So these kinds of things will be missed in the pipeline approach. So what we did is we did a joint approach where we can, by definition, a certain SSLIF is marked as ADE or reason by the relationship it keeps. But by the relationship it keeps with the drugs. So what we did, we replaced all ADEs, reasons, and SSLIFs with a generic concept label in the first stage. Did the same by LSTM CRF. Second stage, the relation classification model actually determines whether something is an ADE or reason or an SSLIF. So that is a little novelty that we did. So and then we have some details on how we did the training, how we did the negative sampling to get the negative samples, etc. So these are our results. So from the documents with 90 F-score, 0.9 F-score, we were able to extract drugs. And most of the attributes we did really well, like 90s and 80s, etc. But for the reasons, it was only 57 or 0.578. This is with the sequential model. And the ADE, it's even worse, like it's only 0.47. So then we did the joint model, so which kind of like improved the reason and ADE as the examples that I showed. So this is what it is. And similarly for the relation extraction, which is kind of like the end-to-end task, you identify your named entities and also you extract the relations, which is kind of like the overall goal. So for that also we observe the same phenomena. So this is organized as a challenge. So there was a blind set that's like a holdout set by the organizers, and these are the results on the blind set. And then the organizers release the data set, the blind set for writing a journal, etc. So these are the results. 14 teams participated, 28 submissions. Our system achieved second place in NER and first place in the end-to-end challenge. So this is the journal that we wrote to drug safety. So that's the top one is the overview paper of the whole journal from University of Massachusetts, and the bottom one is our paper or the journal that is in the same journal. So if you can see like that, so we are the top system in the end-to-end. Like we beat the other systems by a considerable margin, which is almost like 2%. So immediately there was a next challenge, which is N2C2, kind of like in a month or so. So they started organizing another challenge. So the only difference, as I said, they did not annotate any signs or symptoms, which makes the task harder because you don't have negative examples to train your ADE or reason model. Now, similar data sets, similar phenomena, ADEs for 23% and the relations intersentential, 32% drug reason or intersentential. Same approach same as made, we did that, NER, RE. Then we kind of went like one step further. So what we did, we trained an external model for identifying all the sign or symptoms using made data. So we used made data, we trained another model which can identify all the sign or symptoms in the document, which is kind of like helping auto-generate your data to train better models. So we use that, did the same our joint approach. Then these are our results with the joint approach, we kind of did okay. So for ADE, it's very bad, like it's still 0.38. But then we kind of bring in the model from the made data, so it kind of improved to 0.455. So those are here. So this is all good. So this is for the end-to-end task, it was even worse. So it was only 0.41 on the end-to-end task. So these are the participation results. There were bigger participation, 21 teams, 46 submissions, large number of universities from US and large number of corporations like Alibaba, everyone, people like Alibaba, Philips, etc. participated. So teams from them. So we kind of did okay in this challenge. So we are in top 5. So here is a top 3. So they don't have a lot of significance difference. And here we are. But we did very good in recognizing the ADEs and reasons. So the blue marks indicate the ADE and reason. So if you observe, only one team is better for recognizing ADEs because the challenge is all about ADEs. The attributes, etc. are kind of like add-ons. So, and also for the reason we are in top 3-ish. So that is the overall result that we have obtained there. And then we said like, okay, we didn't do well in this. I mean, we could have gotten first. We didn't do much. So we took some key takeaways though, which is joint approaches perform better than pipeline. Deep learning systems outperform CRF and SVM or feature-based models. Significant improvements is still required for drug ADE and drug reason relation extraction. So, and then we said like feature models can benefit from better encoding schemes that can model sentences with multiple drugs, effectively incorporate the larger context to capture long distance relationships, leveraging knowledge to capture implicit relationships. So that was the transformation to our next work. So in this sentence, you have two drugs, lisinopril 30 mg QHS, metrizapine 15 mg PO QHS, right? But lisinopril is only related to 30 mg. Lisinopril is not at all related to 15 mg, or lisinopril is not at all related to QHS. This was one of the biggest error category for the attributes that we observed. So what happened is system went aggressive and kind of linked lisinopril to both 30 mg as well as 15 mg. And similarly, metrizapine to 15 mg and 30. So there were a considerable amount of mistakes that happened due to this. So what did we do? So with the latest technique, we kind of modeled it a little differently. So the idea is we take the target drug, which is lisinopril in this case, and we provided an encoding scheme that can only mark 30 mg and QHS in this case, and marked all of the others as O's, which are kind of, I am saying the model, only these are related to my lisinopril. And I also provided a tag in the bottom saying lisinopril, you are the target drug. And when we do two things in the same sentence, because we have two drugs. So this is kind of like drug centric. So now we went to metrizapine. When metrizapine is the target drug, only those were activated in the encoding scheme. All the others were O's. All the others were outside, which are like turn off. So we trained the model with these kinds of encoding schemes as a first step. So that is two-step joint model. First, we recognize all the drugs using by LSTM-CRF. Same kind of the same architecture, but we identify only the drugs. Everything is turned off. So only identify the drugs. Now comes the most complicated one, like which is like drug-centric model. So now that you identify drugs, can you identify all the information? Because everything is linked to drug, right? So we want to extract its attributes, its reasons, its adverse reaction. So everything is surrounded by it. So now once you identify the drugs, like can you provide a joint, take the joint encoding scheme that was introduced, aforementioned joint encoding scheme, and take that, and we created one instance per drug mention to train the models. So this can extract all the entities and relations with respect to the drug simultaneously. Pre-trained word embeddings from EHRs, random embeddings from others, and CNN for character to word transformations. So here is another thing that we did, which is kind of like position embeddings. So the position embeddings, we said, hey, this drug is at 0, which is the drug's position. So, and then we said 1, 2, 3 on the positive side and -1, -2, -3 for the negative side. But also we didn't send the one hot vectors, but we actually send the representations of these things to the model. We also said type embeddings by saying like, okay, so this is the target drug. We also said O for all the other words, but one small thing we did is we also mentioned other drug. So if a sentence has two drugs, for one drug we said target drug, for the other one we actually said it's a other drug. So that is the representation that we use. So these two things actually kind of made a difference. Then we proceeded by using, so we expanded this model by using Elmo embeddings, so which is kind of like the contextual embeddings that were created on a large scale. It's an unsupervised model that uses multi-layer neural bidirectional language model on a large corpus. So what we did is we took that model, we trained on the PubMed corpus and the clinical NLP to initialize our embeddings. As a next step, here we are kind of building on like the join model. On top of that, we used Elmo embeddings. Then we used positional attention. So the attention mechanisms were introduced recently. The idea is very simple. It almost, I can say it's kind of like a similarity between two things. So if you are looking at one thing, what is your next attention goes to? What does your eye catch? That's the kind of idea. But this was there for a long time. But once the deep learning world kicked in, it became like a big thing in the past few years. So attention mechanism have been proven to be effective for especially the long distance, because you see one thing. So if the doctor sees lisinopril, his mind actually, or his brain actually searches for things like, hey, is there a cough mentioned? Is there a hypertension mentioned? So that is kind of the attention. So we used, so there were self-attention mechanisms even in our relation classification model that draws the global dependencies of the inputs by capturing the relation of two tokens, which is kind of the similarity. But we kind of modified it and said like position attention mechanism, which kind of builds on top of the self-attention mechanism. I'll show one example like that may help. So here, so the idea is to take the target drug, and we see like what. So once you see the target drug, what do you place your attention on? And once you see the current token, what do you place? Where do you place your attention when you compare with all the other tokens? So you can combine. So that's why it's called position attention. So in the self-attention, you would have had only the second part. It's kind of like similarity between all tokens or all pairs of tokens. But here, we also augmented that with taking the target drug as centric and measuring the similarity between all the current tokens. So this kind of is another build on that we did on the existing model. Next, we did knowledge joint, which is a certain degree of background knowledge is actually assumed, especially in the medical field. So when they're writing the note, the doctors, a lot of things they mention is, so here is a very nice example. So if we don't know, if we don't have a medical knowledge, these two kind of look like the same sentence. He has history of muscle pain on Crestor. He has history of diabetes on metformin. Exactly same sentences, nothing different, except for the disease names and the medication. But if you show it to a layman or person who is not a medical expert, they think they both can be AD, they both can be reason. But if you show it to a doctor, then only they know whether something is an ADR. This is very implicit. So these kinds of things the doctors write. So you need systems that can actually understand this kind of implicit information. So for that, we try to bring in, or like the previous research suggests, like using knowledge bases can benefit these kinds of systems. So what we did, we took a large database. As I introduced, FAIRS has this big database of reports that people or doctors or the healthcare institutions report to it. So we took that database, we created, so this is the database structure. So we have indications in the database, we have outcomes, and on the right side, what you see is like the actual count of information. So lisinopril was in 9,003 cases, in the reported cases, it's not in reality, but in the reported cases, lisinopril occurred with hypertension. So basically, if the patient has hypertension, lisinopril was given 9,003 times in the reports. And lisinopril caused cough to 103 patients. So we took these and created knowledge graph embeddings. So this is the representations that we have created using the, taking those large, the database are huge, like 9 million and 10 million, which will again lead us to a different topic, which is again another research direction that we have been taking. Maybe that journal will come next month. So we are submitting to one of the journals. So this is the overall architecture. Now you have like, based on this large corpus, you have representations for each and every concept that is mentioned in these documents. So the idea is take the RX norms, which is like the medications, and the MEDRA, which is the coding. So these two are coded to MEDRAs and RX norms. Take this information, augment the data with all the concepts that are in the UMLS, which is like a huge resource, and transform the original graph to a word level bipartite graph. And once you have this word level bipartite graph, generate graph embeddings using techniques like line or node-to-vec, which is kind of an extension of word-to-vec. And then this is the overall architecture. So on the left-hand side, what you see is the joint model with Elmo and with the position attention. And on the right-hand side, what you see is the knowledge augmentation part, like how we are taking these knowledge bases and creating and taking those embeddings and augmenting into the deep learning architecture. So here are our results after doing all that. So this is the current state of the art. When I say current, before 2 or 3 months. Now, these are our results. So we actually beat the current state of the art. The current state of the art is 52.95 for the committee. And for which is a committee approach, they use like a lot of models like CRF, BiLSTM, CRF, and then they use mechanisms like voting mechanisms to decide like what label you use for each and every of these tokens. But then we kind of abstain from using the committee approach. We kind of wanted to build like single model and show the value. So these are our results on end-to-end task. And if you can see, like for drug reason, the best is 57.92, and ours is with the knowledge joined, ours is 64.96. And also you can see incrementally improving for each and every of these things. With the joined, we saw 59. When we incorporated Elmo, it kind of improved a little bit, but went down for the AD. I mean, it kind of helped for all the other things. But with the position joined, like once we brought in the position attention mechanism, it improved a lot, like from 3% to 5% in each of these, but not a lot in the attributes though, because they are already doing pretty good. And then the knowledge join kind of improved like 3 to 4% for especially for the adverse reactions. In capturing the implicit things, this says like the EHR nodes are like really implicit, and you need to take advantage of both external knowledges and the techniques that are coming out, like which are like the NLP techniques. I mean, there are latest techniques like BERT, etc. So how do you combine these things, and how do you adapt to electronic health records, or the clinical domain or medical domain is very important. So here is the recent journal that's out there. If anyone is interested. So this is published in JMIR. So it's available for reading. So the key takeaways are NLP is booming in healthcare, which is very good. But the field of NLP is not perfect. As you can see on the left side, the graph is growing. I mean, the number of publications are increasing. There are 500, 600, and it's getting to 700, etc. as the year goes by. But NLP is not perfect, as I said, because it's hard. There are a lot of challenges in AI. There are a lot of challenges in NLP. And then there are a lot of challenges, especially with respect to clinical, because of the things that the doctors do. But NLP can make a huge difference in providing better healthcare for the patients in the future. So this is the future work. So all these studies, all the evaluations that we did are intrinsic, which is kind of relying on precision, recall, F-score, all these numbers, which are well established in the community. But we have to measure like how useful are these, right? Like we have to get to the doctor. So that is a big challenge, considering the EHR systems are a little old, and then there are not an easy way to adapt these kinds of technologies into the EHR system. So there are a lot of challenges, but we have been working with 2 multi-specialty hospitals, which are huge hospitals in US from last few years. But still, there are a lot of challenges. I mean, adaptation is a big thing. And then they are not, even if you get to 80% accuracy, the doctor won't be happy. They will say, hey, this is not working. So that's the kind of world we live in. So what we wanted to do is like take these tools, maybe do like pilot studies, like put it in front of the doctor with the EHR, see if they can use like for 3 months or 6 months, and see if it is useful for them. And if it is not useful, also we will learn a lesson saying, okay, what do they really want? I mean, we can capture all the things that they are using, maybe by using the click properties or click statistics and the time spent, etc. So if you can capture all those things, then we can see, okay, so these are the things they like, these are the things they don't like. This is where we have to do the improvements. These are the new things that they are excited about. So we have to make that kind of progress in this world. So coming to the research perspective, so the first one is more like a commercial perspective. The second one is like the research perspective to promote, the idea is to organize community challenges, which we are actually working this year from our team. Like we are planning on organizing 2 challenges to promote research in the field. So if you can come up with, so if 10 people put together, they can come up with a better solution. If 15 teams, all the experts from the world join the challenge, they can come up with a better solution. So that's the idea. So as I said, like the major part is like integrating these technologies into the EHR systems. Thank you everyone for the opportunity.
Sure.
And special thanks to Dr. Ramanamurthy sir. This is a great opportunity for me.
Thank you, sir. But sir, thank you. Sir, we have some questions from the participants.
Yes, sir.
So the one question is, what are the data augmentation methods in knowledge joint, sir?
Okay.
What are the data augmentation methods in knowledge joint?
So the idea data augmentation. Yeah. Okay. So phase database, like in the phase database, it's already normalized. And what they have is only RxNorm names, and they have Medra. But there are a lot of these vocabularies. It's not only RxNorms it's not only Medras, but there are other things like SNOMED. All these have like different vocabularies, and UMLS is a resource that kind of tries to bring all these vocabularies into one semantic network. So UMLS has put in efforts, like I think it has like 153 knowledge resources, which were built by a lot of these medical hospitals. Like there is ICD-9 coding, there is SNOMED coding. So they want to try to put these things together. So our idea is, because we are not doing at the concept level. So if you have observed here, so we transformed our graph to word level graph. So we transformed the bipartite graph that we have in the original phase to a word level graph, which means like we are capturing the word level similarities here. But if we just use the phase database, you may not have all the words that you want. So maybe I just want to give an example. So in phase database, you may see hypertension, but you won't see BP because it's an abbreviation. But if you expand it to all UMLS resources, you will get the BP. You will get the BP in your corpus as well. So now that you will have a representation for hypertension as well as BP, that kind of helps the overall neural network model. So that's the idea.
Thank you, sir. Second question, sir. One more question only. So you are using rules for sentence demarcation.
Yes.
So can't you use deep learning model for the same? This is the question from one participant.
Yes.
Excuse me.
Let's go there.
Should I? I have a question, Dr. Bharat.
Yeah,
Bharat,
well,
sir?
yeah, I heard that. So I'm trying to go to the slide so I can show like why it's.
Yeah, sure, sir.
This is how doctors search for information in the HR notes. Maybe somewhere, maybe here, like in the deep learning slides.
Nice.
Okay. So definitely we can do that. I mean, it's not like we can do deep learning for this, but the problem is you have to create ground truths for this. So no one is really willing to create any training data for these kinds of stuff these days. Why? I mean, the people are not really investing money in the fundamental technologies. The problem is, think about in the perspective of commercial organization like IBM or someone. So why would they actually invest a lot of money in identifying sentence boundaries, and you can get only maybe 0.5% better accuracy, or 0.05 excuse me 0.05, a minor chance, that too. So people are not really taking big steps, especially in the sentence segmentation or tokenization. And also with respect to EHRs, maybe even with the deep learning models, I mean, there were no systems out there that tried that. There were some things which are for de-identifying the text, and there was a corpus that we have experimented internally. It didn't do much. I mean, we actually tried that within our team. So there is a corpus that is available for actually doing sentence segmentation using deep learning models. It didn't do much like when you actually use the rules. So it's really, it didn't make a big difference, especially for the EHRs. You need rules. You need so the point is, there was a paper from IBM. Rule-based systems are dead. And then after the colon, it says long live rule-based systems. So the idea is basically you can't get away from them. You can just rely on deep learning system also all the time. So that's the answer.
Yeah, thank you, sir. One final question, sir. What are the current state of art technologies for applications of AI in telemedicine, sir?
Sorry, what is the question? Sorry.
What are the current state of art technologies for applications of AI in telemedicine?
So if you can see, this is one application, but the shift is happening for people to consume through their phones rather than providing the technology to the doctor. So it is getting into the hands of us. Us means like people. So things like we have apps that have been developed, phone apps, like where you can track your BP, where you can basically track your whole health history, where you can measure how much stressed you are. There are all these skin conductance applications. So these kinds of things will come in the future, like within your hand. So it will immediately alert you, like it will be a tool with you. So it will tell you, hey, your BP is going up. You have a temperature of this much, basically based on the skin conductance. Because even with the whole COVID-19 situation, the skin, the companies that are working on thermal temperature or thermal recognition using AI technologies are becoming huge. So at least the stock prices are going huge. So the overall idea is like, okay, so if you can put like a thermal recognizer when you go to an airport, so you just walk in, you don't have to do anything. The system will automatically detect your temperatures or skin conductance and tell you, hey, your temperatures are up, so maybe you want like a second scan. So these kinds of things will evolve in the future.
Thank you, sir.
Dr. Bharat? Hello.
Yes, sir. Yes, sir.
Yeah, I have a small this thing because mathematics background. I just want to ask you one this thing. Do you adapt any mathematical transforms for convoluting them issue into a neural network?
Yeah. So if you so this one has actually convolution, sir. So the CNN is convolutional neural network. So
that, yeah.
So the idea is, so there are convolutions that have been done at the character level. So CNNs have been used again for a long time, both in the imaging world as well as the text world. But the only difference is why BiLSTM is better is BiLSTM has a memory component and CNN doesn't have a memory component. So the memory helps BiLSTM CRF remember the long distance relationships. But CNN was used to obtain the character convolutions and represent at the word level. So that's what we did, sir.
In that context, there is a problem with the doxycycline has any adverse effect when you are convoluting them?
Sorry?
Does this doxycycline?
Yes, sir.
Does it have any adverse effect in convolutions issues? With regard to BiLSTM.
So doxycycline, doxycycline is, I didn't get the question, sir. Sorry, sir.
Doxycycline basically a life-saving drug. So when you are using this, does it have any effect of these convolution issues when you are injecting a patient? Right?
No, sir. So this convolution is basically for the text, right, sir?
For text, then also. Thank you.
Yeah, this is only for the text.
It is related with some position and knowledge joints. Actually, in that issue also it matters. Actually.
Yeah, this is all text, sir. This is all text.
Thank you very much. No problem.
Now over to CRK, sir.
CRK, sir, please.
Okay, Dr. Bharat, thank you very much for your state of the art NLP and what is happening in the top research centers in the world. And in fact, it has benefited each and every one of the participants, and you have also taken us through the future scope of work also. So I would like to, on behalf of MGIT, I would like to thank you and all the participants for this inaugural first day series started by Bharat from country Bharat. Thank you very much. Thank you, sir.
Thank you so much, sir. Thank you so much.
Dr. Bharat. Thank you very much.
Thank you, sir.
Great question.
Hello.
Yeah, the technical team can announce that we are going to share the slides and all the information at the end of the session. I think at